Hello everyone. So, after having discussed how we can use trajectories sampled in molecular dynamics simulations to get thermodynamic information on systems and processes, and how sampling problems can get in the way, in the previous sections we have also introduced how we can perturb the systems by introducing a bias potential, and how that bias potential can actually help us in achieving converged estimates of free energy landscapes. So in this section we will discuss different approaches at defining such bias potential in practical cases in which we are interested in computing a free energy surface that we do not know a priori, and then and we have limited information on the states that we're interested in sampling. So we will see how this is done in two different quite popular methods. The first one is umbrella sampling, and it's based on introducing static bias potentials, so bias potentials that depend on the position in collective variable space but do not depend on time. And the second method instead is based on defining bias potentials that change adaptively over time, and it's metadynamics. So let us get started with umbrella sampling. So if you recall, the problem that both these methods are trying to solve is a problem of defining the shape of a bias potential. So last time we have discussed the fact that when we have a free energy surface characterized by metastable states, in this case represented by these A and B basins, separated by a free energy barrier much larger than KT, it's a problem to achieve sampling, and introducing a bias potential can help us. The point we made in the previous video is that in order to achieve a specific probability distribution, we have to have information on the shape of the free energy surface, on the position of the minima, on the position of the barriers. For instance, in the limit where we want to reach a flat sample probability density, so a bias probability density that is constant everywhere in collective variable space, we need to know exactly what the free energy surface, how the free energy surface looks like. So for instance, if we aim at sampling a flat probability density indicated here with this P prime of S, what we need to do is to introduce a bias potential V of S that basically flattens the free energy surface. Of course, if we do not know f of s, we cannot do this. So the question is, when we introduce a bias potential that perturbs the potential energy of the system, how do we define its functional form with respect to V? So how does umbrella sampling tackle this problem? Well, umbrella sampling is based on defining a series of independent bias simulations along a pathway in collective variable space. So the working hypothesis for umbrella sampling is that we have a reasonable idea of an accessible pathway that connects two metastable states of interest. And then if we do, we can actually design a series of bias simulations that allow us to sample extensively these configurations along this pathway. And in order to do that, again, here I'm using this qualitative representation of a free energy surface that has two metastable states, and on this free energy surface, on the path that connects these two metastable states in collective variable S, we are defining a number of independent simulations, 1, 2, 3, and 4 in this example, and all these simulations are initialized in a different point of the pathway that connects the two metastable states, and they're subject to a different perturbation. So they're subject to a different bias potential that typically in umbrella sampling is defined as an harmonic potential in S. So the point is, every one of these windows, every one of these simulations that are typically referred as windows is an independent bias simulation. And last time we have discussed how we can actually treat each one of these simulations. In fact, reconstructing the free energy surface in each umbrella, within each one of these simulations, is based on the perturbation theory approach that we have introduced. And so if we go back to the notes, we can recall that basically the perturbation theory approach that we discussed last time allows us to define the unbiased probability density P0 of S as a function of the bias probability density. So the probability density that is sampled by our model in the presence of a bias. So P0 of S, the unbiased probability density, equals the bias probability density PB of S multiplied by the exponential of the bias potential multiplied by a constant that is the ensemble average of the exponential of minus the bias potential evaluated in the unperturbed ensemble, so in the unbiased ensemble. So in umbrella sampling, we are interested in computing this unbiased probability density in every one of the umbrella that we have defined. So in every one of the windows that we have defined that are characterized by a different potential that we are that we are calling umbrellas. So basically we are interested in evaluating this P unbiased of S in every ith window, where I is an index that runs from 1 to the number of windows. And another interesting and useful thing that we can do is to define this constant that is associated to the free energy to the free energy change induced by the introduction of a bias potential in window I by defining the following relationship. So we define a relationship between a constant Ci and this term as such e to the minus beta Ci equals this ensemble average. So if we do so, and we apply, and actually we compute a free energy surface as a function of S in window I, we get the following expression. So the free energy Fi of S will be equal to minus kBt logarithm of the probability, the unbiased probability in S in window I. And so basically we'll get that Fi of S comes equal to Fi of S biased, where this is the free energy, the effective free energy associated to the perturbed Hamiltonian of the system, so the potential energy of the system U0 of S plus the ith umbrella, so the ith bias potential, and then minus Vi plus this constant Ci of S. So we note that the first and the second term, they are function of S, while the third term is a constant. And it's a constant that corresponds to the free energy associated to the introduction of the bias potential Vi of S in the system. So we are now in the position where we can actually, we have all the tools from our simulation, we have all the tools to estimate these first two terms, 1 and 2, because we know a priori the functional form that defines Vi of S, and we can sample a bias probability density PB I of S from the simulations, and therefore we can compute the term Fi biased of S. So if we know this information, we can actually reconstruct in every window the unbiased free energy surface Fi of S. So let's see how this works in practice. So in this case here, we have our double well potential. So as mentioned, we can define an harmonic bias potential that is located somewhere along the pathway that connects the two metastable states identified by this free energy surface. And this bias potential will be centered in a certain position. In this case, it's centered in minus 0.5 in coordinate S, and it will have a certain width. And the introduction of this bias potential will define window I, so a certain window in the set of simulations that will characterize our umbrella sampling simulations. Then we can repeat this process for several windows that sample the entire space of the collective variable that we are interested in investigating. And for each one of these windows, basically we have defined a different VI of S. Okay, so in green we are looking at the VI of S. In blue it's an analytical expression for the underlying free energy surface. So if we perform independent simulations in the presence of each one of these bias potentials, what we get is that we can reconstruct the bias free energy, so what I called FIB in these notes. This bias free energy surface, the effective free energy surface associated to what is sampled in your simulations, is this Fi biased of S, and we can reconstruct it in a straightforward manner using this expression here, basically, and plugging in the bias probability density. So if we do that, we obtain these light blue estimates, and we can do that for every window. But as you can see, of course, these are not our final answer, and in order to get our final answer, we have to include, basically we have to account for the presence of a bias. So we have to introduce the bias potential that we know and we have defined. So this is the bias potential that we need to account for, and so basically if we do that, we can obtain an estimate, a local estimate of the free energy surface, which is represented in red here. So basically in this equation we are now basically computing this free energy surface Fi of S from the terms that come from the bias probability density sampled in every independent window and the bias potential defined in every window. So as you can see, these free energy surfaces that are defined locally in every window, they're not really aligned. They do not allow us to compute a global free energy surface that reconstructs correctly the blue line. So what is missing? Well, the term that is missing is this set of constants Ci here, that are defined one per window, one per simulation, and that are not determined, cannot be determined independently in each of the windows. They cannot be determined this way because the free energy surface, the global free energy surface that we need to compute, it's actually used to compute this ensemble average. So this ensemble average already contains information on the global unbiased probability density that we don't have yet. So essentially we cannot get these constants from each individual simulation. So in practice, what we need to do to solve this problem is to take on the different estimates of the free energy surface that have been reconstructed locally from the sampling obtained in every window, and align them in such a way that we can reconstruct a global free energy surface. And the alignment will be obtained by correctly estimating the constants Ci defined in every one of the biased windows. A popular approach that is typically used to define these constants and to compute the offset of the probability densities, compute the offset of the free energy surfaces defined locally in every window, it's called the weighted histogram analysis method, or WHAM. And I'm going now to sketch a bit the idea behind WHAM and how it works. Weighted histogram analysis method allows to obtain a global free energy profile that covers all the configurations that are sampled in different windows by computing a weighted average of the probability density obtained from every independent simulation. So basically, if we call Pi of S the probability density in the ith window, and we call instead P of S the global probability density, we have that P of S is computed as a weighted average of the Pi of S's. So as the sum, as a weighted sum of the Pi of S, with I that goes from window 1 to the total number of windows in the system. Now, the weighted histogram analysis method has developed a particular expression for these weights Wi that allows essentially to minimize the error associated with the estimate of P of S. And that minimization of the error is obtained by applying the Lagrange multiplier technique and using as a constraint a condition on the weights. So basically the weights, as they should sum to 1. So basically the sum of all the weights from 1 to n windows should sum to 1. So the weighted histogram analysis method has solved the problem of determining the weights that minimize the error on the P of S, given the constraint that the sum of the weights has to be 1. So the expression of the weights that is obtained by the weighted histogram analysis method is the following one. So the weight in window I for configuration S is equal to the number of samples that are obtained in window I multiplied by e to the minus beta Vi of S minus Ci, where Vi of S is the bias that is applied to window I, and Ci is the constant that we have discussed earlier. And at the denominator, we have that since these weights have to sum to 1, we will have a sum with index j in this time, j that goes from 1 to the number of windows of the same quantity, and j multiplies e to the minus beta Vj of S minus Cj. So let us now take this expression obtained with the weighted histogram analysis method and plug it into this sum and see what happens. So if we do that, basically we have that the probability density, the global probability density P of S becomes a sum that runs for I, it goes from 1 to n number of windows of the weight in the separate windows, and if we take one of these terms, we'll get that ni e to the minus beta vi of s minus ci multiplies now pi of s. And at the denominator we have the usual sum e to the minus beta vj s minus cj. Now at the numerator we can now recognize that this term actually corresponds to the bias probability density in window I. So the global probability density has now become a sum of quantities that we can directly evaluate from our simulations, except for the constants Ci and Cj in the denominator. So this is j that runs from I. Okay. So basically now we have that that sum becomes PS becomes the sum I that goes from 1 to the number of windows of ni pb I of s. So the number of samples from window I multiplied by the bias probability density in window I function of s multiplied by the denominator to the Bj, Cj, this is all to the minus 1. So we have this expression now of PS that depends on the bias probability density that we obtained directly from simulations. It depends on the number of samples that we can obtain from simulations, so quantities that we know from our simulations, and depend on the shift constants, on the essentially on the free energy associated to the introduction of the bias in every window, Cj. So the question now is, how can we actually compute this quantity? To compute this quantity, we can go back and look at the definition of Cj. So Cj, as we've shown earlier, here is defined as from the ensemble average of e to the minus beta vi of s. So we can actually look at computing explicitly this ensemble average now that we have an expression for P of s here. So let's do this. We have that e to the minus beta ci equals the integral of e to the minus beta vi of s in the s multiplied by the probability density P of s. So now these two equations that emerge from this analysis, this is the first one and this is the second one, actually provide a set of equations that can be solved self-consistently to estimate the shifting constant Ci, and iteratively then compute the global probability density and proceed in this iterative manner until self-consistency is reached and there is no and a sufficiently small relative change in the constants Ci is actually obtained. So the idea is we perform a number of bias simulations in the presence of local umbrellas that generate a certain probability density that is biased and that we use in this expression, using some initial guess for the shifting constants. Then from this expression we compute a global P of S, which will be incorrect, but then will be used to estimate, to provide a first estimate of the constants that will be then plugged again in this expression, and these two sets of equations will be solved iteratively. Something that I'd like to point out is that these constants Ci, so these terms, will be window dependent. So there will be one of these equations per every window. However, the PS is the global one. So this is not the unbiased probability density in window I. It's the global unbiased probability density. So it's the P of S indicated here on the left side of the equal sign. We have now seen how umbrella sampling allows to reconstruct free energy profile, global free energy profiles from independent bias simulations in which a perturbation in the form of an harmonic potential is introduced, and then how WAM allows us to take the reconstructed free energy surfaces in each of the windows and patch them together to obtain a global free energy surface. So the combination of umbrella sampling and WAM is an effective way of computing a potential of mean force. However, a prerequisite of this process is that one has to have a reasonable guess for a pathway, a physical pathway that connects two metastable states of interest. So if this, how can we get around this problem? One way of getting around the problem of identifying a specific path that connects two metastable states is to actually allow for the adaptive exploration of a collective variable space and the construction of a bias potential in an adaptive manner based on this exploration. A method that implements this idea is metadynamics. And metadynamics allows to essentially construct iteratively and adaptively a bias potential that increases the chances of leaving metastable states, exploring pathways that connect those metastable states to other metastable states, and in the process allows to compute free energy surfaces. So the qualitative idea behind metadynamics is that if one has the usual double well free energy surface projected along a certain collective variable that is characterized by two local minima, one actually starts by exploring a minimum, and while it's exploring this minimum, the metadynamics algorithm constructs a bias potential that is pushing the system away from the minimum, and it does it by essentially increasing the potential of mean force projected along the collective variable of choice, so by introducing a potential that disfavors the configurations that have been already visited, and in the process actually enhances the fluctuations of the system along that collective variable. So as you can see here at time instance 1, a metadynamics algorithm would push the system up in energy and then up in energy again until a transition is observed and the second metastable state is identified, and the process goes on exploring the collective variable space. So in order to try and understand the details of how this this process actually is propagated along molecular dynamics trajectories, let's go and discuss how the bias potential associated to metadynamics is adaptively constructed based on the configurations that are explored from a trajectory. So the potential at time t can be indicated as a function v that depends on the position in collective variable space S and of time t. And such potential is defined as the integral of all the Gaussian contributions that have been added in S up to time t. So we can write it as the integral between 0 and t of these Gaussian contributions. These Gaussian contributions are defined as omega that multiplies exponential of are defined by a Gaussian in collective variable space that has a thickness, that has a width, sigma, and it's centered around a position that is visited at time t prime. This Gaussian is multiplied by an energy rate omega that is given as the ratio, that can be defined as the ratio between the height of the Gaussians, W, and the characteristic deposition stride of the Gaussians that we can indicate with tau g. So in normal standard metadynamics, these two parameters are constant, so the height of the Gaussians does not change in time, and also the stride does not change in time. Hence we have that this energy rate is constant, Gaussians are added up to time t and accumulate in collective variable space, resulting in an exploration of the collective variable space and allowing to estimate the free energy surface as the opposite of the bias potential modulo a constant. So in standard metadynamics, we can recover the free energy in collective variable space as V of S and T that tends to infinity. So basically, at long times, the bias potential converges to the opposite of the free energy in collective variable space, modulo a constant. Now, this is really practical because if we can afford to run a simulation for a sufficiently long time, such that it can explore all the relevant metastable states projected in S, we basically get out an estimate of the free energy surface projected along those collective variables, along S. A problem that's associated with standard metadynamics, and that we will comment on by looking at an example later, is that in a single run, the bias potential does not converge modulo a constant to the free energy, but rather oscillates around it. And then basically this has two consequences. The first consequence is that the bias potential, as it's constructed, overfills the underlying free energy surface and basically keeps pushing the system towards higher energy regions of the collective variable space. So essentially, if the simulation runs for long, we will start sampling regions that are always that become higher and higher in energy, and basically have a lower and lower probability, and therefore a lower and lower relevance in defining relevant ensemble averages. And the second thing is that it is not trivial then how to decide when to stop a simulation. So when this convergence modular constant can be considered satisfactory. One criterion that is typically used to evaluate whether sufficient sampling has been obtained and it's possible to stop a metadynamic simulation is whether a diffusive behavior of the system along a collective variable S is actually observed. So a variant of metadynamics that actually allows to tackle this overfilling problem and actually introduces a convergent behavior of the bias potential is the so-called well-tempered metadynamics method. So this method is actually based on introducing a time dependence for this energy rate omega that we just discussed. So let me just tidy up here. If we move this here, so this is the behavior of standard metadynamics, where the energy rate is constant and the free energy estimate is obtained as the opposite of the bias potential in the long time limit. In the case of well-tempered metadynamics, instead, the energy rate omega changes over time, and it changes over time due to changes in the height of the Gaussians that are deposited. In particular, the height of Gaussians deposited in position S and time t in well-tempered metadynamics is defined as omega tau g that multiply an exponentially decaying function of the bias potential V of S and t. So this exponentially decaying function is function of depends on one parameter, delta t, that has units of a temperature, and it's an arbitrary parameter that modulates the behavior of well-tempered metadynamics between two extremes. So when delta t diverges, well-tempered metadynamics tends to standard metadynamics. While when delta t vanishes, the well-tempered metadynamics tends to the unbiased dynamics limit. So essentially, by manipulating delta t, one can choose the rate at which the height of the Gaussians decay, and therefore one can choose essentially an energy scale that is sampled by the metadynamics algorithm. Moreover, introducing this behavior for the height of the Gaussians actually introduces a convergent behavior in the bias potential V of S and T, and a precise relationship between the bias probability density that is obtained in the long time limit in a well-tempered metadynamics run and the parameters that appear in this exponential decay, in particular delta t. So in this case, in the case of well-tempered metadynamics, the final estimate of a free energy surface function of the collective variables is still a function of the final bias potential, but it's slightly different than in the case of standard metadynamics. And in particular, we get that the free energy is a rescaled version of the final bias potential with a minus sign in front of it. In particular, we get that in well-tempered metadynamics, the bias potential Vs in the long time limit equals minus delta t divided by t plus delta t So in the well-tempered case, the bias potential converges to a rescaled version of the free energy surface, but knowing the characteristic parameter that introduces this decaying behavior of the height of the Gaussians allows to recover a free energy surface in the function in the space of the collective variables S. Let's now compare how does the bias potential evolve in the case of well-tempered and standard metadynamics for the simple case of a double well potential, similar to those that we have analyzed in the case of umbrella sampling and in the previous videos. So this is a video that is taken from YouTube, and it's been produced by Giovanni Bussi, and it actually contains a comparison between a standard Langevin dynamics on a double well potential that does not involve any metadynamics, a plain metadynamic simulation, and a well-tempered metadynamic simulation. So you can see that, first of all, while the system that is simulated without introducing any bias is stuck in a metastable state, and it's sampling its configuration space in that metastable state, the biased simulations actually can can get out of the metastable state and can explore the collective variable space by finding and find other metastable states of relevance. On top of that, however, you can appreciate the different behavior of the bias potential that is being deposited over time. In standard metadynamics, the system keeps evolving until it reaches this limit in which the bias is not converged, but it's stationary. Basically, it's evolving modulo constant. So it's able to reproduce the opposite of the free energy surface modulo constant. In the well-tempered metadynamics case, instead, the bias potential is evolving towards a limit in which it reaches a shape that is that corresponds to a rescaled version of the free energy surface. To conclude, in this third video, we have looked at two different strategies to introduce a bias potential in a molecular dynamics simulation to achieve enhanced sampling of the configuration space and essentially to converge free energy surfaces for the system of interest. The first of the two is umbrella sampling, and is based on using these perturbation ideas to obtain the unbiased probability density from the biased probability density computed from independent simulations, and then using methods such as the weighted histogram analysis method to patch them together and obtain a global probability density. The second, instead, is based on introducing a history-dependent adaptive bias that evolves over time as the system explores new configurations in collective variable space, and allows to obtain the free energy surface at the end of the simulation or in the long time limit as a function of the final bias potential. These are not by all means the only two methods, but they kind of capture the spirit of two different classes of methods based on a static bias potential and on an adaptive bias potential. And in the tutorial session next week, what I aim to do is to build a connection between these methods and thermodynamics integration approaches, and see how thermodynamic integration can actually be applied to both umbrella sampling and metadynamics-like algorithms. And of course, answer any question that is related to these first three videos. So thanks for your attention, and see you next week.